Let's take a few minutes and talk about the labs that go along with the gauges section of your course. Okay, we have Lab 8A, we have Lab 8B, and then we have a reading gauges exercise. So let's start off by talking about Lab 8A. Now, I can't demonstrate the lab for you, but I can actually give you some hints that will actually walk you through the process and tell you a little bit behind the reason. Okay, you're going to put your manifold gauges on systems probably 100 times, 200 times a year. Okay, it's going to be one of your most frequent tools you use. Should it be? Probably not, because we can do a lot of the same stuff with our thermometers. Because remember, gauges, all they do is tell you the temperatures where the refrigerant is boiling and condensing. However, you're going to use your gauges. Every time you put your gauges on and off a system, you are losing refrigerant because there's always some left over in your hoses and everything else. So every time you lose refrigerant, your system loses some operating efficiency. So it's really important that the amount of refrigerant that you take out of the system that's caught in your hoses is at a minimum. So the whole purpose of today's labs is to get you to take your gauges on and off a system in two different methods without losing a lot of refrigerant. Okay, so we're going to start here with Lab 8A. The objective is to complete this exercise. You'll be able to remove your manifold gauges without losing any refrigerant. Again, any is too tight of a word, so let's just say minimal refrigerant loss. Okay, so what we're going to have you do is start and let the unit run for approximately 5 to 10 minutes. Now, if the system has only the king valve on the high side, in other words, a service valve on the high side and a service valve on the low side, I do not want you to use your low loss fittings. And we're going to change step D a little bit, okay? However, if your service valve has a Schrader fitting, that's one of the ones that looks like a bicycle tire core, I want you to use your low loss fittings. Okay, so what I want you to do is go ahead and put your gauges on the system. I want you to jump out the pressure control. This is pretty important. The low side, not the high side. I want you to jump the low side of the pressure control. Just put a wire across or an alligator clamp across the two terminals of that terminal strip. Now, I want you to, if you're using low loss fittings, and this is only if you're using low loss fittings, remove the high side hose from the high side. If you are directly on a service valve, I want you to front seat that high side service valve. Okay? Do not remove the hose if you're not using low loss fittings. Okay? So again, in step D, if you are using your low loss fittings on a Schrader valve, remove the high side hose. If you are using no low loss fittings and you're on a service valve, front or back seat that service valve to close the service port. Okay, remember, back seating is all the way out and it closes the service port. Now, you're going to open the valve on the high side of the manifold. Then you're going to crack open the low side manifold, okay? Because what you're going to do is basically take liquid refrigerant that's caught in that high side hose and feed it back into the system on the low side. Now, you're going to reduce the low side pressure until the gauge indicator reaches the first marking on the gauge face above 0. Now, what we're doing here is basically it's pumping down the system. You're not going to get it that low, okay? So what we want you to do is I want you to leave the gauges on in step G until both gauges are at the same pressure, not the needles in the same place. Both gauges are in the same pressure. Then go ahead and shut down the unit. Either remove the low side hose if you're using low loss fittings, or open the service or close the service valve so you can pull the hose off. Okay. Step J is not required in this procedure, okay? So just be aware, step J, you don't have to do in this procedure. Prove to your instructor that your refrigerant gauges have no refrigerant in them other than you might have a little bit of a gas in it on the low side, very low pressure. The questions on this lab all surround your gauges, your fittings, and your service valves. Okay, why must you have low loss fittings on the high side? Okay, to prevent refrigerant loss if you have a Schrader core. 3 positions of a service valve: front seat, back seat, mid seat. Why must you jump out the low pressure control in this procedure? Because if the refrigerant pressure drops too low, it's not going to completely pump down your gauges, and it's going to trip the low pressure control. By the way, did you remember to remove the wire from your low pressure control, the one you jumped out? Okay, D, how much refrigerant can your hoses hold if not pumped down correctly? It can be as much as 32 ounces of refrigerant depending on how long your hoses are. Let's just say probably for the answer here, anywhere from 12 to 32 ounces of refrigerant can actually end up in your hose. That's a lot. Okay, there's no drawing for this lab. Now, Lab 8B is another version of this same thing. Okay, this is teaching you how to manually pump down a system by jumping out the low pressure control. Now, here's the reason we do this. Occasionally, you have to change like a filter dryer. You might have to change a metering device. You might have to do something in the system that is after your receiver or condenser, but before your compressor. What this does, it actually takes all of the refrigerant in the system and it contains it between your compressor discharge and your receiver outlet. Only do this if you have a receiver or a very large condenser. Okay, mainly we only do this if we have a receiver. If you do it anytime else, you have a real chance for damaging your compressor. Okay, so as usual, we're going to start the unit and let it run for approximately 5 to 10 minutes. Okay, I want you to put your gauges on here. It's pretty important. It doesn't say it in the steps, but if you don't put your gauges on here, you're actually going to lose refrigerant and let air into the system. Okay, so just be aware of this. Go ahead and manually pump down the system. What you have to do that is you have to close or front seat the valve on the receiver. Now, when you do this, okay, it's basically screwing that valve in all the way on the receiver, but your gauges have to be on the system. If you do this without the gauges on the system, you're going to lose all the refrigerant out of that king valve. So what you're going to do is you're going to close or front seat the valve on the receiver. You're going to bypass the low pressure control. What front seating it does is block the refrigerant from leaving the receiver. So your gauges and the refrigerant, okay, is what's in the cycle system. Run the system and the pressure on the low side drops to about 1 or 2 psi. Stop in the system and wait to see if the pressure rises. If so, pump the unit down again. Because of how our trainers are set up in the shop, you may have to do this 2 or 3 times. The system is manually pumped down when the system holds a pressure on 1 or 2 psi on the low side and the service valve is front seated on the receiver. Show your instructor the receiver. Okay. Now open and back seat the receiver valve. In other words, push it back to the back and watch the pressure on the low side rise. Crack open the low side manifold valve. Try the pump down operation for a few times. I really want everyone who's working together to get a chance to do this. Once you feel confident, have your instructor watch you perform this procedure and have them initial this lab. So, what's the purpose of pumping down or jumping out the low pressure control during manual pump down? Because the low pressure control is going to be set over 1 to 2 psi and you will not be able to get the system to stay running long enough if you don't jump it out. By the way, did you remove the jumper that you put on in an earlier step? Where's the refrigerant stored during the pump down operation? Primarily the receiver, but the condenser should be listed as well. Okay, it's the receiver and the condenser. Why do we want to be able to manually pump down a system? Is if we need to service anything between the receiver and the suction return to the compressor. So in there would be your sight glass, your metering device, your filter dryers, your evaporator, anything on that side of the system. we can service, then we can evacuate the air out of it, and we can let the refrigerant charge back into it. What would happen to our manual pump down operation if we did not jump out the low pressure control? Well, as I said, it would never achieve 1 to 2 psi because the compressor would trip on low pressure. What would you have to do if after manual pump down the pressure rose on your low side? Well, we talked about it up here. If it rises again, okay, if the pressure rises, pump the unit down again, turn on the compressor again, and let it continue. Okay, is there another way of doing pump down operation besides doing it manually by closing the receiver valve? Yes, if your system has a liquid line solenoid valve, you have the ability to trap the liquid by de-energizing the liquid line solenoid valve. It will still trap it between the liquid line valve and the outlet of the compressor. You just will not be able to service as many parts in that if you have to. There's no drawing on this lab, so that page can be left blank. Okay. Now, the next exercise that was on this day was to do some gauge exercise. The first one, I wanted you to pick any refrigerant. Okay, any refrigerant at all. I wanted you to take a 28 psi low side and 100 psi high side and convert it to temperature. So let's just pick one. Okay, so we have 100 psi high side. Okay, we're going to use, let's use, let's skip 410 because there's some weird things with that. Let's go over to R23. No, that's, let's do R500. We have 100 psi on our high side, so that's very close to 80 degrees. And what did I say I had on the low side? We have 23 on the low side. So again, 80 degrees on the high side. Let's get that filled in. And just so we know what refrigerant we're using. And then on the low side, okay, we are looking for 28 psi. So 28 psi is about 21 degrees. Let's say 21 degrees because it's right there. And if you want to see how I did that, you come over here. I said 28 psi is about that area. And come over to the left-hand side and you get your temperature. Okay, and then I gave you a couple more of these. Some of these that I filled in the refrigerant. So now you got to find R134A. And that's going to be the blue, the baby blue. We want to come down here. It's 22 psi and 149 psi. So we have 22, which is right about there. That's 25 degrees. Okay, so we can come over and we can put the 25 degrees. And then we have, what did I say it was? 149. We have 149 psi. Okay, which is very, let's just say 140, right there, 147. So we'll say 110. Okay, because again, you use your closest number. Okay, and again, what we did is we basically went over to the column. I found the pressure in the correct column. Okay, so it was 149, so it's right there at 147. I came over to the left side, and it's 110 is my closest number. I probably could have gone to like 111, but there's a real temperature difference between 110 and 115, or a pressure difference. So let's just stay with the 110. So that's what the reading gauges exercise is. Come through, do all of these. Now, on R410A, I need you to be a little bit careful because some pressure charts actually use two temperatures for R410A. Okay. I think this one didn't. Okay, R410A is being used in residential air conditioning, but some temperature charts will have a liquid and a vapor pressure. My vapor side is my evaporator. Okay, my liquid side is my condenser. So just be aware of that, is that some may have two columns, and that's because of a really excessive temperature glide because of the blend. Okay, so I think that gets you on the right direction for some of these labs. Again, just be careful with the 8A especially, that you actually know which fitting you're using. It's either Schrader gets low loss, service valve does not get low loss. Again, Schrader fitting gets low loss fitting, service valve does not. And don't do that lab 8B without putting your gauges on those service valves, or you'll have refrigerant all over the place. Hope that helps. Let's talk about the assignment of the day, or the schematic of the day, number 8. Now, when we look at this assignment, what we are seeing is we have um, 2 evaporator fan motors, 1 CFM that's a PSC, 1 CFM that's a CSIR. We have a compressor that's a CSCR, and we have a line voltage thermostat that shows everything. Now, the assignment does say that we do want you to show all the components and the motor, the schematic. We want you to go ahead and draw this out in PDF Expert and submit the file. So let's take a quick look at one way of doing this. Okay, I've already drawn the base for this in PDF Expert. Okay, we have my line, we have a service switch. Even though it doesn't say it in the schematic, we have to have something that actually controls power to this. I have my cooling thermostat drawn in. I decided to draw it in on the side, okay, because I felt that it would be a lot easier to deal with that way, and it would give me more room for everything else that I need to get in here. Okay, so the first thing we're going to do is let's go ahead and deal with putting in our 2 evaporator fan motors. We have one that's a shaded pole motor, that's EFM1, and we have one that's a split phase motor. Now remember, split phase motor, we still have to take out the start winding. So let's go ahead and draw my 2 motors in. Let's start with, we're going to go ahead and start with the shaded pole. That's easiest to draw. I'm going to go ahead and put it, let's just draw it right here. Okay. Now, shaded pole, remember, has 1 winding. Okay. So we'll go ahead and label this one EFM1. Okay, that's shaded pole motor. Real easy. Okay. So let's go ahead, and then we're going to go ahead and draw my split phase. Now, I'm going to go ahead and draw it up here because it really doesn't matter. I'm going to pull power from there. So what we have is we have a we have a run terminal, a start terminal. Okay, I am going to go ahead and use, let's use a centrifugal switch, which is a normally closed contact. We're going to go ahead and draw my windings in. Okay, and then let's go ahead and get some lines in for my power. Now remember, we only supply power to the run terminal, right? Because the run and the start are connected together through that centrifugal switch. And then we'll take this back to, I'll take this all the way back to neutral. It really doesn't matter, but now let's go ahead and label this thing. Okay, so this is EFM2. And we have run. We have start. And we have common. Okay, and remember down here, even though it's just 2 windings, we still have a run and a common. Okay, because it's just 2 terminals. So that's my evaporator fan motors. Now we got to deal with my condenser fan. My condenser fan motor 1 is a PSC motor. Okay, PSC motor, remember, has a permanent split capacitor. So that's going to have a run capacitor between the start and the common. Okay, so I'm going to go ahead and come down here. Let's go ahead and come down here. And we're going to go ahead and I will draw in my 3 terminals, put my windings in, and let's go ahead and put in my run capacitor. Actually, let me make that wire a little neater there. Actually, let's neaten that whole little disaster up. My run winding. Okay, then let's go ahead and put my lines in. And we will get rid of that excess line there. Make sure everything connects. And then let's go ahead and label this. This is CFM1. And we have my run. We have my start. We have my common. And let's just label the run cap. Okay, so we have a PSC motor. Okay, now the next motor is my CFM2, which is supposed to be a CSIR. Now remember, capacitor start, induction run. So I have to have some sort of start component that takes out my start winding, okay, and the start capacitor when the motor starts to run. Okay, now we have a variety of different start components we've talked about, but let's go ahead and I am going to go ahead and we'll put the motor up here, okay, because it just, again, is an easier situation. So we're going to go ahead and use the current coil. Now remember, the current coil relay, okay, gets its power or gets energized via a coil that's in series with the run winding. So let's go ahead and put my motor in. Okay, so now we have my start run. The only thing I'm missing here is I have to have my normally open contacts and my start capacitor. Okay, so what I'm going to do is then we will go ahead and connect it. Let's connect this into the circuit using some straight lines. Okay, we'll come out of run. Okay, now if we'll go ahead and label this. Okay, now we're going to have two designations up here because I have an M, okay, and I have an R in the same place. I have my S, I have my start capacitor. Let's go ahead and I'm going to move that designation for that start right there because I want to put an L right here. Okay, so we have my start relay components there. Okay, so everything inside this set of dots is my start. Okay, so but let's just go ahead and I'm going to get rid of some of those dots just because it makes it doesn't really show up well. But remember, that's inside one component. Okay, so I have my L, M, R, and S. Okay, the only thing that I haven't done is I didn't label that my CFM2. Okay. Now our one missing component here is our CSCR compressor. Now I'm going to go ahead and put that in down here. Now CSCR means it has both a start relay or start capacitor and a run capacitor. It also has to have the start components to remove the start capacitor from the circuit once the motor reaches the 75% of the running load. Okay, so let's go ahead and we're going to go ahead and put in my, I'm going to go ahead and put in my run cap first. Okay, then I'm going to go ahead and label my run. I'm going to go ahead and throw my common label in. And I'm going to go ahead and throw my start label in. Okay, and let's go ahead and label run caps just so we don't forget about it. Okay, now, common in this, or my motor's neutral, just draws straight in. Okay, now coming out of run, okay, we're going to, again, power run directly. Okay, run, oh, in this case, gets direct power. So we have my run capacitor now. So we're at the PSC point. However, now what I need is I have to have my start capacitor. Okay, so what I'm going to use is I'm going to use the current sensing relay. Okay, or the potential relay in this case. So remember, I'm going to have pin 1 come through a normally closed contact. Then I have pin 2. And then I have a coil that comes to pin 6. So let's go ahead and label that. Or pin 5. Let's go label that again. Okay, so 1, 2, and 5. Okay, now 5 connects always to common. Okay, 2 connects to my start winding. And then 1, we're going to put in my start capacitor and connect it to line. Okay, so let's go ahead and label the start capacitor real quick. Okay, because remember, this whole relay is based on back EMF. Okay, so my potential relay, which is this down here, and let's go ahead and we'll go ahead and just put a box around this for the hell of it. Okay, that component there, the potential relay, okay, is what takes out my start component. And remember, it works on back EMF. Okay, so we now have all our motors and everything labeled here. Okay, so you basically, this is our diagram. Okay, what we were looking for was a shaded pole motor, 120 volts, a split phase motor, 120 volts for my evaporator fans, a PSC motor, 120 volts for my condenser fan 1, a CSIR motor for my condenser fan 2, a CSCR motor for my compressor, a line voltage thermostat that controls everything. So there's the diagram.